over kind of some of the basic background of neural networks and some of the basic mathematics so that we can sort of understand the process of how neural networks function. And then we'll look at a really simple application of a regression analysis done using a neural network. So I think the first thing that's maybe a little important to talk about is just some overall vocabulary. And a lot of times these terms get thrown around and nobody really understands how they relate to each other, right? So sort of the big terms that we want to consider are artificial intelligence, machine learning, and deep learning. And how are these different from each other? So artificial intelligence we really think of as being this larger category, right? It's almost like an umbrella that machine and deep learning sit within. And artificial intelligence covers a range of topics, including neural networks, but also including robotics and statistical tests. Machine learning specifically encompasses types of algorithms that are largely data-driven and statistically based. This does include neural networks, but also includes decision trees or clustering methods like random forest or k-means clustering. Deep learning specifically has to do with neural networks, and we'll look at a couple of different types of neural networks over the course of this seminar. Today what I'm going to focus on is a simple type of neural network called a multi-layer perceptron. Or sometimes people call them feed-forward networks also. It's a type of feed-forward network. So let's talk about just some overall examples of deep learning and really what deep learning means. So specifically when we're talking about deep learning or machine learning, we're talking about data-driven models. And what I mean by a data-driven model is that as opposed to using a computer to simulate a physics-based or analytical equation, what we're really doing is showing the computer a series of cause and effect relationships. And we're showing the computer hopefully enough of those relationships so that it can uncover the underlying mapping from how to get to the cause to the effect. So that hopefully if you have a well-trained neural network, what you do is you supply the inputs or the cause and hope that you get a predicted effect that is within your acceptable accuracy limits. So with enough training, you hope to get close to human performance, and of course that's based on how accurate your training data is to begin with. And that comes from advanced pattern recognition. So one example would be looking at, in the medical field, at X-ray images. And so, if you have enough examples of, say, an X-ray with a particular physical malady, right? X-ray with, a tumor in the upper right corner or something like that, and you show the computer enough examples, hopefully what the computer will be able to do over time is to recognize that pattern and be able to make that diagnosis. Another example would be translation from one language to another. You guys on your smartphones, every time that you're talking to Siri or every time that you're using your microphone to translate text, you're using a neural network to do that actually, to predict that speech. And of course, I think we've all heard about these self-driving cars that people are trying to develop, and there have been successes and failures, I think, commensurate with the expectations that we all had for self-driving cars on roads, which might be a wonderful thing. But, another advantage to creating a neural network is that although they take an extraordinarily long amount of time to train, once you have a well-trained deep learning model or neural network, those terms are synonymous. But once you have a well-trained deep learning model, it works very, very quickly, and you can get it to run in a fraction of a second on a laptop computer. And so you have a decrease in both computational time and a decrease in user and model bias, because we're really allowing the data to do the talking as opposed to coming up with an analytical equation that could introduce some bias into the analysis. So really, artificial neural networks are in essence modeled after the anatomy of the brain. And so what we think about is we think about having two different neurons passing some type of electrical impulse or information in between, right? So I have neuron A, and I'm going to pass an electrical impulse to neuron B, and I have some type of output. So now what I want to try and do with my neural network is I want to try to replicate that behavior. So I have an input, and I have an output. And I'm assuming that these are more or less correct, right? And what I want to do is send an electrical impulse from my input to my output, but I don't get the expected behavior. So the question is, what changes do I need to make to my inputs in order to be able to get the expected output from my network? And this is really similar, if anybody has gone through a traditional sort of Bayesian inversion calibration exercise or a data assimilation, we're really talking about overall the same workflow of what changes do we need to make to our existing data so that we make predictions that are closer to the predictions that we know or assume to be true, right? So here's just a quick example of maybe how this process works in sort of an overall kind of sense. So I have this known function, y equals 2x plus 1, and I have some data that I've generated from this function, right? I have my x data, which is going to be my input to the function, and my y data, which is the evaluation of the function at all of these points x. So what I'm going to assume is that I don't actually know the function itself. And what I want to be able to do is to try to uncover the function given the input and output data alone. So my task is, given this data, what I want to do is find the weights and biases that I need to apply to my input data x to be able to get my estimate for y hat. So let's try this a couple times. So this is just a quick graph of what our true function is that we're actually looking for. And we're going to run through a couple of trials. Now in a neural network, we would call these trials epochs, and I'll explain that a little bit more in the next couple of slides. But for epoch 1, we're going to make an assumption that our initial weight is 1, our initial bias is 0, and go ahead and plot that function. RMSE is going to be the error metric that we're using, and that's root mean squared error. So it's the root mean residual, essentially, between our true data, the data that we're trying to predict, and our y hat, or data that we did predict. So let's try again, because obviously that's not a very good fit in this sense. So on the second epoch, I'm going to increase the weight and bias to 3 and 0.5 respectively. And you can see I get a much closer fit. My RMSE, or my error metric, has decreased, which is what I want. I want this value to approach 0. But I still don't have a very good fit. And so I'm going to try one more time. Actually, you would try it thousands of times, right, in a neural network, but for the purpose of the presentation, we're going to do 3. So in this case, I actually decrease my weight and increase my bias. And now, having made those changes, I actually have a perfect fit with an RMSE of 0. So this is an example, kind of a cartoon example of what a neural network might look like. Really, when we're talking about a deep network as opposed to a machine learning type neural network, is really the number of hidden layers in between. And let me explain what I mean by that. So on the very far left side, I'll have my input data. On the very far right side, I'll have my output data. And those are going to stand for our initial and final layers in the neural network. Everything in between those layers is what we would call a hidden layer. And that collection of hidden layers is what we use to represent what we call the latent state, or the system state, as we move from our input to our output data, or our cause to our effect. And what's happening between each of these hidden layers is that we're passing information between each of the nodes in the layers. You'll notice that these layers are made up of little circles, and what we're going to call those circles is individual nodes, or our individual nodes. And those individual nodes pass information, or what we're going to call activations, between the nodes in the current layer and the nodes in the next layer. So here's another picture of that again, with our inputs over on the left side and our outputs over on the right side, standing for our initial or cause information and our final layers or effect information. And in between these layers, I have a number of hidden layers. So I'm going to go through the process of how we work with neural networks. The first thing that you really want to do is called data partitioning. And what that means is that I have a large volume of what I'm going to call training samples, or cause and effect relationships, right? I have a large volume of data that I'm going to use to teach this computer how to recognize a cause and predict an appropriate effect. And what I want to do is I want to partition approximately 90% of that data to use to train my model, but I want to reserve a small amount of data to be able to test that trained model to see if my model can predict as well on known data as it can on unknown data, or data that it has never seen before, samples that it has not been shown before. Traditionally, you do about a 90-10 split, but depending on the volume of data you have, often in the geosciences, we're a little bit more limited because a lot of our data is observational or comes from monitoring networks. And so you may have to adjust that split a little bit, and that's definitely something to experiment with a little bit. So during the training phase, I'm going to call this step 1. It's actually a 2-step process, but during this training process, what we're doing is we're trying to predict y hat such that the residuals between our predictions and our true known data are minimized. And what we're really looking for is this mapping, theta, applied to x, a function of those parameters that will give us this y hat or prediction. So the first step in the training process is called forward propagation. And that's where I'm working from left to right, processing my inputs and trying to make my prediction y hat. When I make my prediction y hat, what I'm going to do is calculate those residuals between my y and y hat as a function of the weights and biases that I applied to my input data to make my prediction y hat. The next step of the training process is called back propagation. And in the back propagation process, what I want to do is to find the changes in my cost function with respect to my weights and biases that I need to make on my next epoch or my next pass through. So one epoch is one forward and backward pass. It's like swimming a lap in a pool, right? It's all the way forward and all the way back. And so what I'm really looking for is to minimize this cost function over these epochs so that I minimize the residual between y and y hat. Does anybody have questions at this point? Okay, we can come back to it too if you do, or if you change your mind. So after the training process is complete, step 2 is to test and evaluate the performance of the model on the reserved data, or that data that the model had no access to during the training process. So now I just want to go over a little bit of the notation here. Remember that I said the information passed between nodes and layers is called activations. And so this is a little bit of the mathematics of how an activation is actually calculated and the way that we talk about the notation. So in this sense, the activation is going to be A. Sigma is the activation function that we're applying to the weighted linear combination of our input data. And we'll talk a little bit more about activation functions in just a moment. A sub k with the superscript L minus 1 is the information from the previous layer, or the activations from the previous layer. So what we're always doing is we're taking previous information, applying a weight and a bias, putting an activation function around that, and passing it to the next layer. W sub k comma n is the weight for the current layer, and B sub n is the weight, or excuse me, is the bias for the current layer. So let's talk about activation functions just a little bit. There are a lot of activation functions that you can use in your neural network, and I think, much like coming up with the parameters for a semi-variogram in geostatistics, coming up with some of your hyperparameters or choice of activation function is a little bit of the art of creating neural networks, right? And so it may be an iterative process to figure out what works the best for you in your particular application. But there are a couple of things to note. So up here I have 2 different activation functions plotted. On the left is called the sigmoid function, and on the right is the ReLU, or rectified linear unit function. So the sigmoid function has been, I would say, the more traditional approach to an activation function, or the hyperbolic tangent is also another popular function. But one thing that I do want to take note of is that notice at the extreme tails of the sigmoid function that the slope of that function actually approaches 0. So during the back propagation step, when we're taking the derivatives or partial derivatives of all of the functions we applied in forward propagation, we then have some issues when those slopes approach 0. The rectified linear unit has actually been a major breakthrough in activation functions. Practically, it means that there's a threshold for activation after which there's some linear response that we're assuming. And it's a linear simplification that has allowed some of the training steps to really speed up quite a bit and to avoid this issue of a 0 slope. So I have a little bit of I would say this is my mathiest slide that I have so far, but it's the same type of cartoony approach that we looked at earlier with our input data here, our output data in this case. I just have a single node for my output data and a hidden layer in between. So we can just look at some of the actual mathematics of how information is passed from the inputs over to the outputs. So remember I said that we're passing activations in between each layers. So that activation is going to be denoted as A, and we're going to apply that function, that activation function sigma, to a quantity Z, which we're going to define as that weighted linear combination. So Wx plus V, the weight applied to our input data plus a bias. We're going to call that quantity Z. So we're going to wrap that, whatever activation function we're using. You can actually use different activation functions with different layers if you kind of really want to mix it up. And we're going to pass that information to the next layer. So we consider A with the superscript capital L to be the final layer activation, which would be equal to y hat in this case. So y hat is going to be equal to our activation function applied to the weighted linear combination from our final layer. We're going to calculate the loss. In this case, I'm just using the squared residuals, right? But you can also coming up with your loss function can be a little bit of an art or some trickery to do. So I'm going to calculate the loss between each sample, and I'm going to take usually the mean of the loss for every sample, and I'm going to call that my cost function. Now you'll notice here that it looks like I'm calculating my cost function really as just a function of y, but I have the cost of, with respect to w and v here. Well, remember that this y is actually a function of z, which is a function of w and v due to that weighted linear combination. So what I really want to do now is I'm going to do that back propagation step. And what I'm going to do is I'm going to take the partial derivative of this cost function with respect to both weight and bias. And I want to use those to update my weights and biases from the previous epoch on my next forward propagation step. And there's one parameter I haven't talked about here, and that's this alpha parameter that you'll notice at each of these update steps. And the alpha parameter is called our learning rate. The learning rate is actually one of the most important parameters in this optimization step. And let me show you why. So the learning rate is what creates the overall step size during our optimization process. So let's assume that this surface shown here is the surface created by our loss, or what we'll consider our cost function. What we're going to do is we're going to start at probably not getting very good residuals, right? Our initial guesses or our initial y hat predictions probably aren't going to be very effective. And so what we're going to do through the optimization process is try and find the steepest gradient, right? That's what we do when we take derivatives. We're trying to find the steepest gradient along this surface to be able to find the global minimum. That's what we're really looking for, is the global minimum. The problem is, though, that if your learning rate is too large, you might take a step in the wrong direction. And then eventually you end up minimizing to a local minimum as opposed to a global minimum. The problem with minimizing to a local minimum, obviously, is you could have done better, you could have had better accuracy. And so a lot of times adjusting that learning rate over time is really important. And I can show you guys how to do that. I don't think that I do it in the simple example today, but we can certainly look at that later. So today, this is the example that we're going to go over today. And You guys obviously have the code to be able to do that, but one thing that I do want to do today is to talk about the overall structure of the code and maybe how that relates to what we've gone over so far. So this is actually going to be on 2 different slides just to make the text large enough. But this initial step here is really just creating and subsetting data. So you'll notice here that the first thing that I'm doing, whenever you're using Python, you have to import all of the packages or libraries that you need. You should have these already downloaded on your computer, otherwise you'll get import errors. So the first thing I'm doing is I'm bringing in the deep learning framework, Keras, that I'm going to use, and I'm really just bringing in the pieces from that framework that I'm going to need. You could, of course, bring in the whole framework if you wanted to. I just like to not tie up my memory with a bunch of unnecessary tools that are probably very, or not particularly space conservative. So that's one thing to think about. sklearn or scikit-learn is a pre-processing, well, I use pre-processing tools from that framework. It's also a machine learning framework. And then I bring in this data processing package called NumPy. It's one of the more, or I think you're supposed to say NumPy as in Python, right? But it's one of the more popular data processing packages. And I usually bring that in under the short name NP because it's less typing, and that's a traditional way to bring in NumPy. So the first thing I'm going to do here is actually, because you know, this is just an example, I don't have real data, so I'm going to make up some data, right? So the first thing I'm going to do is I'm going to generate 100,000 random numbers, and I'm going to call that my X data. And I'm showing that here in yellow as I've been showing it in previous slides. And I'm going to just apply the squared function. So the function that I'm going to try and predict is y is equal to x squared, right? So I'm going to create my y data by just squaring my x data, and I'm showing that here in purple. And now I'm just defining one of the shapes, so the number of features of each of those arrays, meaning in this case the number of columns. Now what I'm going to do is that data partitioning. Remember we talked about splitting up our sample data into a 90-10 split or a train and test split of our data. And so what I'm doing is I'm taking the first 90,000 rows and I'm assigning those to my y and x, or x and y training sets, and then the remaining data is assigned to my testing data sets. So we've now gone through, let's see, data creation and, in this case, partitioning. And this is the function that we're predicting with this data over here. One important thing to actually notice about this, and I'll talk a little bit more about this later, is that, actually, does anybody have an observation about the distribution of this data?
It's not linear.
Okay, so it's not linear. This is actually just the function y equals x squared, which is a nonlinear function. What I actually want to point out here is that this data is actually plotted as little black circles, right? So obviously there are some sections that have little black circles that are overlapping or that are much closer together. So I have many concentrated and near continuous data samples throughout most of my function. However, close to the tails of my function, I have fewer data points. And so really that's going to be an interesting thing when we run the neural network, because those will behave like outliers or extreme values. But let's get back to the code really quickly. So now what I'm going to do is, in this amount of code, I'm actually writing that neural network that we've talked about in the picture. So, you know, if any of you guys have experience with computer programming, you know that your codes can get really long really quickly, right? In most of the deep learning models that I have right now, you know, my actual code to make the model is probably, you know, almost always under 100 lines long, but my script to run it might be, you know, 500 lines long because 300 of those lines are plots, right? So plotting takes up a lot more coding space than actually making the network. And this, of course, is because we're using the frameworks. If you were to hard code a neural network on your own, which I certainly recommend if you've never done it, I think it gives you a lot of, just a really strong understanding of how information is passed from one layer to another, forwards and backwards. But you know, the frameworks are really doing a lot of the heavy lifting in terms of the code. We're just applying functions or modules from those frameworks where you know, the actual implementation in terms of typing is relatively short. So what I'm going to do, at the very top I've defined some what I call hyperparameters. So hyperparameters are sort of parameters about parameters, right? In this case, what I'm defining is the number of epochs, or the number of forward and backward passes I'm going to make through the network during the training process. And a couple of other parameters that I haven't talked about too much yet, but that we will talk about probably in the next, I think, session. And those would be batch size, dropout rate, and the number of nodes per layer. And I've arbitrarily assigned 64 nodes per layer. You'll notice that, computer programmers, and this is just a side note, but computer programmers tend to use arbitrary values like 32, 64, things that are in nice sort of bite-sized, unintended increments, right? And, oftentimes in Python, do you guys know why Python is called Python, by the way? It's a Monty Python reference, right? So all this stuff is just created by incredible nerds, and so you'll see a lot of times people will use an initialization value of 42, which is, again, another sort of nerdy joke. Hitchhiker's Guide to the Galaxy, yeah, it's the, spoiler alert, right? It's the, the secret to the universe. I think it's supposed to be the number 42. Anyway, that's just a side note. So now in the code, what I'm going to do is I'm going to, remember I created that input data. What I have to do now is to create the structure of a deep learning model, or really what I'm going to call a graph, right? I'm going to create a graph network that is basically going to be the shell that we're going to pass our data through during the training process. But right now what I have to do is set up the structure. So the first thing that I'm going to do here is I'm going to create basically a shell to put my input data into, right? And I'm going to do that using this input layer from Keras. And I pass it a couple pieces of information. Most importantly, I need to let it know the shape of data to expect. And we'll talk again a little bit more about that later. Now what I'm going to do is I'm going to create a hidden layer. In this case, for this network, I only have one hidden layer. We could certainly make it a much deeper network, but it's just much simpler code this way. So I have one hidden layer here. Again, I'm letting it know how big I want that layer to be, or the number of nodes I want to have in that hidden layer. And I'm letting it know the activation function that I want to use within that hidden layer to pass information forward. Now what I'm going to do is I'm going to create my output layer. And again, I'm going to make sure that I let it know, that I let Keras know how big I need that layer to be, or the number of nodes, which would be equal to the number of features that I'm trying to predict, and which activation that I want to use. And now what I'm really going to do is just compile the model. So here, in these three blocks, creating the input, the hidden, and the final output layer, I've created the structure for my entire network graph. So now in this second column, what I'm really going to do is I'm going to inform Keras which data sets I'm passing in to represent my inputs and outputs, and some other options that I need to set during the model process. So what I'm doing here in the model statement is specifying the names of the data sets that I'm passing in. And you'll notice that I gave my input the name main input, and I gave my output the name main output. And so I'm instructing Keras that those are the shells that I want to pass in at a particular point in the graph. Now what I'm doing is I'm compiling the model, and I'm specifying, what I'm calling an optimizer. In Keras, an optimizer, there are a number that you can use. Normally it's a regularization technique. And regularization is a technique that you use to avoid overfitting, or I think more simply put, to avoid the mapping being a memorization of your training samples. And we'll talk a little bit more about regularization, I think, in the next coming sessions. This fit statement that I'm applying to my model object, I'm storing as the variable history. This will be a dictionary later on that you'll have access to and that you can use for plotting and wonderful things like that. But what I'm actually doing in this fit statement is this is where the training of my model actually occurs. So if I only wanted to just run the piece of code that was going to train the model, it would be this fit statement right here. And in this fit statement, I'm passing in the training data that I'm going to use to train my model. I'm going to let it know the number of epochs that I want to go for. Again, batch size is another regularization technique that we can talk about. And in this case, I'm also passing in the validation data. Now here's one, and when I say validation data, what I'm really talking about is that test data that I partitioned away earlier. So here's one thing that's really important to note, is that in Keras, when I'm passing the validation data in during my training process, I'm not actually using that test or validation data to do any of the training with. The reason that I'm passing it in during my fit statement is that what I want to do is I want to be able to, at the end of my training process, I really like to make a plot of the loss during training and the loss during test over time, or on my training data and on my testing data over time. So what's going to happen is at the end of every epoch during the training process, what Keras is going to do is it's going to evaluate the model on the test data without informing the model using the test data. Does that make sense to you guys? So the test data isn't actually being used to train, but what I'm getting is a metric of its performance as I move forward, right? And that for me is really helpful because no matter how well the model is doing on my training data, what I really need it to do is to do well on my testing data. And so I want to be able to look at that over time. And that's a very traditional approach. And then what I'm doing here, after that fit statement, is I'm actually just going to see how the model did on some new data, right? So in this case, it looks like I actually just made a new random data set of X, but usually you would put the actual test data in there. So I think, yeah, okay, cool. So I think this is the last slide before the demo. So these are the actual results. Remember I told you that I like to be able to have the loss for training and test over time. I do that because I like to be able to make these plots because it's really, really helpful to visualize your results. In this case, this isn't that dramatic of a training exercise in that we had data that matched up very, very well and had essentially no noise in it. But generally, this is what you will see in an overall trend is that your model will tend to learn very, very quickly in the first couple of epochs and then very slowly over the rest of your training period. And in this case, we have I used, I think, mean squared error for the metric, and we did pretty well between the Y and Y hat or the training and test set. So I'm very happy with how that worked out. So let's look now, unless anybody has questions, we can move into actually watching how that demo is able to run. Excuse me. Okay. So this computer is, what you're seeing me move around here is actually my workstation back at my desk. I have a remote. This is how I sort of jerry-rigged the Python install issue, is that we're actually just looking at a portal of my real